It's time for Maths with Mr. Thomas.
How we doing so far, okay? Here we go, chapter 4, lesson number 4, separating the variables for, Chitiri, mathematical models. In other words, worded problems. So, often we have to apply our knowledge of differential equations to solve worded problems. For example, we may be hit with, boom, something that looks like this. Looks very worded. So, example 14, examples 1 to 13 are in the previous 3 lessons on differential equations. So, the number of strands of bacteria, X, present in a culture after T days of growth is given by the differential equation 1 over x dx equals k dt. Part A, find the general solution for x in terms of t. And part B, given that there are 326 strands initially present and the number of strands observed after 4 days is 1,833, estimate the number of strands likely to be present after 1 week. So, how do we start this one off? Well, the first thing we want to do is find the general solution for x in terms of t. In other words, we want to get down to x equals. How do we do that? Well, to do that, we need to solve our differential equation. So to solve the differential equation, what's the first thing that you would do? Separate the variables! You got it, you would separate the variables. However, you can see for this one that the variables have already been separated. Ain't they kind? So you've got x's on one side and you've got t on the other. So we don't need to do that part. So we're just leaving it as 1 over x dx equals k dt. From there, after the variables have been separated, although in this case we didn't need to, you would then integrate both sides. So we would integrate 1 over x with respect to x and integrate k with respect to t. So let's do that. If you integrate 1 over x, what would you end up getting, Matthew? Perfect, you would get ln x. If you integrate k, what would you end up getting, Liam? Perfect, you would get k, but because we're integrating with respect to t, you'd have kt. And what else would you have, Ian? Perfect, you would have plus c. So we've got ln x equals kt plus c. We want to get down to x equals, but just now it's ln x. So how do we really get rid of this ln? We would use exponentials. You got it, use exponentials. So if we take e of both sides, we'd have e ln x equals e to the power of kt plus c. But if you look here, you've got e to the power of something plus something, so you can split that up. So you're left with e to the power of ln x equals e to the power of kt. And what would you do here? Brilliant. You'd multiply them together. So you're multiplying that by e to the power of c. Just remember, e to the power of c, you wouldn't write e to the power of c, you'd swap it with a. So you'd have e to the power of ln x would equal a e to the power of kt. And final step, e ln, well, one's an exponential, one's log, they're the inverse of one another, so they would cancel, leaving you with x equals a e to the power of kt. Moving on. Part B. Given that there are 326 strands initially present and that the number of strands observed after 4 days is 1,833, estimate the number of strands likely to be present after 1 week. So whenever you're given something like this, the first thing you need to do is read through it and think about what you're being told. So because it starts off telling us that there are 326 strands initially present, well, initially present means right at the start. And we know right at the start, the time is going to be 0. So when t equals 0, x, the number of strands, is going to be 326. And therefore, we can use our answer from part A, x equals a e to the power of kt, and we can swap t with 0 and x with 326. So we get 326 equals a e to the power of k times 0. And k times 0 is just going to be 0, so we'd have a e to the power of 0. And that would equal 326. We all know everything to the power of 0 is going to be 1, perfect, so it leaves us with a equals 326. So we now know this value of a. We can therefore rewrite this equation as x equals 326 e to the power of kt, because we know this value of a. The next thing it tells us is that the number of strands observed after 4 days is 1,833. So we know that after 4 days, so in other words, when t equals 4, the number of strands, x, is going to be 1,833. So we can sub them into our equation. So our equation, remember, is a e to the power of kt would be x. So we can replace x with 1,833. We can replace t with 4. And a, well, we don't need to leave it as a anymore. We can replace that with the 326, as I just said, because we know that value. Therefore, we've got 326 e to the power of 4k equals 1,833. We need to find the value of k, so first off, divide both sides by 326. So e to the power of 4k would equal 1,833 divided by 326. To find the value of k, how would you do it? Perfect! If you take logs of both sides. Because we're working with e, use log base e, or in other words, your natural log. So you'd have ln e to the power of 4k would equal ln, and then this fraction here. However, if you think about that, you'd have ln e to the power of 4k. You could bring that power down, so you'd have 4k times ln e, and remember ln e would just become 1. So you'd be left with 4k. So 4k would equal, and then remember you took the log of the other side as well. So it's ln 1,833 over 326. We need to find this value of k, so k is just going to be ln, that fraction, divided by 4, or in other words, a quarter of ln, that fraction. And if you put that into the calculator, bump, 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 you get 0.4317 to a few decimal places. Therefore, our equation is going to be x equals, we know a is 326. And we've just worked out k to be 0.4317, so we can replace that as well. So it'll be 0.4317t. Just make sure you put t to quite a few decimal places so you have it very, very accurate. From there, we can use that to work out this next part. It's saying how many strands are likely to be present after 1 week. Well, after 1 week, we know that's 7 days, so we can replace t with 7. Therefore, we'll have x equals 326 e to the power of 0.4317 times 7, which works out to be 326 times e to the power of 3.0219, which will give us 6,693. And you can finish that off with a nice little story that says, therefore, after 1 week, there is likely to be 6,693 strands of bacteria. Lovely. And that's your answer. Example 15. Once again, looking at this before we even read it, it is one of these massive problems. It's very worded and it's very off-putting, but you need to go through it, read the information, and then try and solve it as best you can using all the skills that you have learned. So, reading it first of all, according to Newton's law of cooling, the rate at which an object cools is proportional to the difference in temperature between the object and the surrounding medium. When an object cools surrounded by air at a temperature of 75 degrees, the cooling of the object is governed by a differential equation of the form d capital T over d small t equals negative k times capital T minus 75, where capital T is the temperature of the object after small t hours of cooling and k is a constant. So part A, find the general solution of this differential equation expressing t, capital T, as a function of t, lowercase k, t. Part B, given that a certain object cools from 125 degrees to 100 degrees in half an hour when surrounded by air to a temperature of 75 degrees, find the temperature of this object at the end of another half hour and find the time taken for the temperature of this object to fall to 80 degrees. So the first thing we want to do is find the general solution of the differential equation. So we're looking at this equation here and we're thinking, how do we find the general solution? Well, we know that in order to find the general solution of a differential equation that is of this form, we would, perfect, you separate the variables. The last example, the variables were already separated. We didn't have to do that. But in this one, you can see that you have capital T on both sides. So we need to have capital T on one side and lowercase t on the other side. So doing that, multiply both sides by dt, the small t, and then divide both sides by capital T minus 75. So we end up with 1 over t minus 75 dt equals negative k dt. Make sure you don't mix up the capital T and the lowercase t. You can see here the variables have been separated. Woo! What do you do next? Integrate. Perfect, you would integrate both sides. So we're going to be integrating 1 over t minus 75 with respect to capital T, and we're going to be integrating negative k with respect to lowercase t. So integrating 1 over t takes 75. How would you go about doing that? Help us out. Perfect, you would have ln t take away 75, and that would equal, if you integrate negative k with respect to t, so Hannah, what would you get? Brilliant, negative kt. And in the end, we've got plus c. We want to have it as capital T equals, and we're wanting capital T as a function of a small t. So we need t equals. How do we get that? Well, the first thing we need to do is we need to think it's trapped in brackets. Oh no, with ln. So let's get rid of ln, and to get rid of that, we would use our exponentials. So you'd have e to the power of ln t minus 75 would equal, and because we took the exponential of one side, we have to do the same at the other. So we'd have e to the power of negative kt plus c. From there, well, you know eln will cancel out, so we'd be left with t takes 75 equals e to the power of negative kt plus c. And we also know that because we've got e to the power of something plus something, well, we can multiply them together. So we'd have e to the power of negative kt times e to the power of c. Just remember, don't leave e to the power of c as e to the power of c. Swap that with a. So t minus 75 would equal a times e to the power of negative kt. Therefore, t, if you get that on its own, that will equal 75 plus ae to the power of negative kt, or ae to the power of negative kt, and then plus 75. That is our general solution. Part B, given that a certain object cools from 125 degrees to 100 degrees in half an hour when surrounded by air at a temperature of 75 degrees, find the temperature of this object at the end of another half hour, and find the time taken for the temperature of the object to fall to 80 degrees. Because this is part B, we're probably going to be using our answer for part A. In part A, we had to get the general solution, so that is what we found here, dancing about. Hello! We're also told a lot of information here. So what we need to do is take time to read over that information and use it to find both the values of A and K. A and K are just going to be constants. So if we're given this information up here, we can use that to find what these constants would be. So the first thing, an object cools from 125 degrees to 100 in half an hour. So we know that if it cools from 125 degrees, then right at the start, when t equals 0, the temperature is 125 degrees. That is what it's starting at. So the time is going to be 0. So we can replace t with 0 and capital T with 125 in here. So 125 would equal 75 plus ae to the power of negative k times 0. We know that negative k times 0 would just be 0, so we're left with e to the 0, and anything to the power of 0 is just 1. So we have 75 plus a equals 125, and therefore a is going to be 50. We are told that it cools from 125 degrees to 100 degrees in half an hour. Remember, the time is measured in hours, so when the time is going to be 1/2, it's half an hour, then the temperature of the object is going to be 100 degrees. So we can use that as well. So 100 would equal 75 plus a e to the power of negative k times 1/2, just swapping t with a half and capital T with 100. From there, if you subtract 75 from both sides, you would have a e to the power of negative k times 1/2. That would equal 25. And we just worked out that a is 50, so we can replace a with 50. So we'd have 50 e to the power of negative a half k would equal 25. From there, in order to find out the value of k, we would have to use logs in order to bring that index down. But we can't do that when we've got the 50 here. So first of all, divide both sides by 50. So we'd have e to the power of negative a half k would equal 25 over 50, which is just a half. From there, if you take the logs of both sides, we'd have natural log ln because we've got e. So we'd have ln e to the power of negative a half k would equal ln 1/2. But on this side here, we'd have ln e. We can use the index rules. We can use log rules to bring that index down. So we'd have negative a half k times ln e. But ln e is just equal to 1. So we can just write that as negative 1/2 k, and that would equal, remember we took the natural log of this side as well. We want to find out the value of k, so to get k, well, we'd multiply both sides by 2, and we'd also multiply through by negative 1 as well. So we'd have negative 2 ln 1/2, and if you put that into the calculator to a few decimal places, you get 1.3863. Therefore, it means our equation, because we've found the values of a and k, we are going to have t equals 75 plus a is 50, so we'd have 50 e to the power of, and replace k with 1.3863. So it'll be negative 1.3863 t. And that there is our equation. And we can now use that equation to answer both B part 1 and B part 2. We want to find the temperature of the object at the end of another half hour. So at the end of another half hour, we'll think about what the time will be. It's already cooled from 125 to 100 in half an hour, and after another half hour, well, that will be 1 hour in total that will have passed. So 1 hour will have passed, or in other words, t would just equal 1. So we can replace t here in this equation with 1. So we'd have t equals 75 plus 50 e to the power of, and we've got this negative 1.3863 times 1. If we're multiplying that by 1, it's just going to stay as it is. So we'd have 75 plus 50 e to the power of, and then that will give us 87.5. And that is going to be the temperature. So that'll be the temperature of the object at the end of another half hour. B part 2, find the time taken for the object to fall to 80 degrees. So we know that in order to fall to 80 degrees, well, the temperature is therefore going to be 80. And if we know the temperature is 80, we can use this equation here and we can replace t with 80. So we'd have 80 equals 75 plus 50 e to the power of negative 1.3863 t. And we're wanting to find out what small t would be. The first thing to do is subtract 75 from both sides. So we'd have 50 e to the power of would equal 5. And then from there, divide both sides by 50. So we've got e to the power of, and that would equal 5 over 50, which simplifies to 1/10. We are wanting to find this value of t. So to find the value of t, we're going to have to find a way to bring that down. And to bring it down, you would use logs. So because e is involved, use natural log. So we'd have ln e to the power of negative 1.3863t would equal ln 1 over 10. And from there you could bring that index down and you'd be left with that negative 1.3863t times ln e, but ln e just becomes 1. So that would leave us with negative 1.3863t, and that would equal ln 1 over 10. So we're taking natural logs of both sides, bringing the index down, and then ln e would disappear, leaving you with that index. To find the value of t then, we would have ln 1 over 10 divided by that decimal there. So t would equal, and that becomes 1.66. Therefore, you can finish that off by saying it will take 1.66 hours for the temperature to fall to 80 degrees. And that is your answer. Example 16, when a valve is opened, the rate at which the water drains from a pool is proportional to the square root of the depth of the water. This can be expressed by the differential equation dh by dt equals negative k times the square root of h, where h is in meters is the depth of the water t minutes after the valve was opened, and k is a positive constant. So part A, find the general solution of this differential equation. And part B, given that the depth of the water in the pool was initially, so right at the start, 9 meters, and after 20 minutes of draining, the depth had dropped to 4 meters, how long did it take to drain the pool completely. So part A, find the general solution. Well, how would we start off doing that? We are given this differential equation, and in order to get the general solution, first of all, we have to solve it. So to solve it, we want to start by separating the variables. So we want h on one side, t on the other. So we'd end up with, if we multiply both sides by dt, dh equals negative k times the square root of h dt. And then from there, if you divide both sides by the square root of h, you'd have 1 over root h dh equals negative k dt. So we can see now that the variables have been separated. Woo! So you can integrate both sides. So we're going to integrate 1 over root h with respect to h, and we're integrating negative k with respect to t. We obviously have to rewrite 1 over the square root of h as 1 over h to the power of a half, and then we can bring that up to the top, so we'd have h to the power of negative a half. You have to write it in that form before you integrate. So integrating that, if you'd have h to the power of negative 1/2 and you integrate, add 1 to the power, divide by the new power. So that will give us h to the power of a half divided by a half. That's the same as timesing by 2. So you'd have 2h to the power of a half equals negative kt plus c. Therefore, we can say that 2 times the square root of h, so 2 root h, would equal negative kt plus c, or rewriting that, c minus kt. So that there is the general solution. Part B, given that the depth of the water in the pool is initially 9 meters, and after 20 minutes of draining, the depth had dropped to 4 meters, how long did it take to drain the pool completely? Well, again, this is a part B, so we're probably going to be using this answer. And we're also given quite a bit of information. So we want to use that information in order to find the values of these constants, c and k. So to do that, we want to think, right, well, the first bit of information it tells us is that initially there's 9 meters. So initially means when t equals 0, right at the start. So when t equals 0, the height is going to be 9. That's how much water is going to be in the pool. Therefore, we can replace in this equation t with 0 and h with 9. That will give us 2 times the square root of 9 equals c take away k times 0. K times 0 is going to be 0, and it leaves us with c equals 2 times the square root of 9. Square root of 9 is 3, so it's 2 times 3, so c is going to be 6. We are also told that after 20 minutes of draining, the depth had dropped to 4 meters. So after 20 minutes, well, t is going to be 20, and h, the height, is going to be 4. Therefore, if we go back to the equation again and we replace t with 20, and we replace h with 4, we'll have 2 times the square root of 4 equals c minus k times 20. We know c is 6, so we can replace c with 6, so we'd have 6 take away k times 20, or 20k. That would equal 2 times the square root of 4. Square root of 4 is 2, 2 times 2 gives you 4. So it's 6 take away 20k would equal 4. Therefore, 20k must be 2, and k would equal 1/10. Therefore, the equation, we know c is 6, and we know k is going to be 1/10, so our equation becomes 2 root h equals 6 minus 1/10 t. Or if you want to rewrite it, you can just move the t to the top there. So 6 minus t over 10. So that is our equation. We are asked how long it takes to drain the pool completely. So if you think about it, when the pool is drained completely, what's the height of the water? Brilliant, it's just going to be 0. So to drain the pool completely, the depth or the height of the water must be 0. So we can say that when h equals 0, we'd have 2 root 0, we're just replacing h with 0, that would equal 6 minus t over 10. Square root of 0 is 0, times that by 2, it's still 0. So 0 would equal 6 minus t over 10. Therefore, t over 10 must be equal to 6. Therefore, t would equal 60. And you can finish that off by saying, therefore, it will take 60 minutes, or 1 hour, to drain the pool completely. Try some of these questions. That is 3 examples looking at the worded problems with differential equations. Try separating the variables for mathematical models in the Unit 1 booklet from page 87 to 90. Any problems? Let me know. Best of luck. Bye. Have fun. Adios. See ya.